Assalamualaikum and good morning. Okay, topic today is integration and differentiation. So what is integration? Integration is a way of adding slices to find the whole. Okay, integration can be used to find areas, volumes, center point, and useful things. Integration involves differential elements. Okay, differential element we have dl, ds, and dv. Integration is a way of adding slices. Okay, for example, graph like this, fx, this one is x. Okay, what is the area? Area under the curve. So let's say we start from here, from here, from here. What's the area? How to find the area under the curve? We can use slices. We can make a rectangle in this under the graph, under the curve, rectangle, rectangle, this rectangle, rectangle, this rectangle. This with the delta x, okay, this one is x, so delta x, this one is fx. So we can add all the rectangle together, it will become area. Okay, add all the rectangle. This is delta x. However, we can see that there's still a space here. So this not accurate, not very accurate. How to make it better? We can reduce the size of delta x. Yeah, reduce the size, this one, reduce. So maybe you can use like this. Smaller one. So we add all the rectangle, it will become total the area under curve. Okay, however, still have a space there. So how to make more accurate? We have to reduce delta x to reduce very small, extremely small, nearly zero, but not zero, nearly zero. Okay, very small. Very small. Okay, very small. So, and we add all this area, it will very accurate. Okay, this one is very small, extremely small, delta x. So now we can write as dx. Okay, this one is a differential. Okay, differential. We call down this differential elements, differential of x. Okay, x, fx. This one we call integration, integral. Or, sorry, let's say this one is point A, point B. We can use integration, area equal to from A to B, fx dx. Okay, dx means that the differential, the differential of x. This one also we can see that this is a combination of differential equation and also integral and differential derivative. Okay, next is differential elements. Okay, this is what I mentioned before. Differential element is infinitesimally small. Means that very small. the size of dl, for example, is differential length. The size of length is very, very small. Nearly zero, nearly zero, but not zero. Nearly zero, the size of d. The size of delta very small, nearly zero. What is differential element? Differential element is generated by making small or differential changes along the direction of the unit vector in a particular coordinate system. Coordinate system, let's say we have that we learned in the last lecture. Coordinate system, we have three coordinate system: Cartesian, cylindrical, and spherical. Let's say Cartesian coordinate system, we have x, y, and z. Y, x, and z. Cylindrical, we have x, y, and z. So let's say we have Cartesian, and this one is cylindrical. Cylindrical and Cartesian. Okay, for cylindrical, we have x, y, and z. So the definition of differential element is, differential element is generated by making small or differential changes along direction of a unit vector in particular coordinate system. Small changes. This is D. We have for Cartesian, they have x, y, and z vector. So for small changes for x vector, we call dx. For y, at y vector, we call dy. For z, we call dz. This one is small changes along vector. Cartesian, for Cartesian, we have x, y, and z. For cylinder, cylinder, we have r here. R is radius, the distance between z and point P. Okay, this one is r. This one is phi. For coordinate, for cylindrical coordinate, we have r, phi, and z coordinate. So in this case, for Cartesian, we have dx, we have x, y, and z. So we have dx, dy, and dz. And then for cylindrical, we have r. The changes of r, we call dr. Here. Changes of r are all here. Small changes of r, we call dr. R, z, the small changes of z, we call dz. And then phi. Okay, for phi, let's focus in this part. Okay, phi. Let's say we have, try to zoom here, zoom this part. This is our phi. This is r. Okay, this one is x-axis. Okay, here. X-axis, phi, and r. The changes of phi changes is here. This one, arc length. This length is due to changes of phi. This length we call arc length. Arc length is equal to R d phi. Okay, d phi is here. Okay, R d phi. This one, R d phi. The changes of the phi will become R d phi. The distance changes. Okay, for Z is dz. For R is dr. For Cartesian, changes x dx, y dy, z axis dz. For cylindrical R, the changes is dr, phi, changes is r d phi. This one is arc length. Sorry, this one is phi, phi. And then z, the changes dz. Okay, this is to show the differential element making small differential changes along the direction of the unit vector. Okay, in particular coordinate system, we know that for Cartesian x, y, z, for cylindrical we have r, phi, and z. So changes of r is dr, changes of phi is r d phi. Yeah, this one is arc. Changes are arc. This changes. When phi changes, this length of arc equal to r d phi. And then the changes of z become dz. So now what is a different length? Differential length. dl, differential length. Okay, so for Cartesian, dl equal to dx plus dy plus dz. dx plus dy plus dz. For x, vector is x hat, y hat, direction of this one is direction of vector. Okay, vector x, y, and z. This one is z. For cylindrical, dl equal to dr plus r d phi plus dz. This one. We add all. R plus r d phi plus dz. This one is direction of r is r. Direction of r d phi is phi. Direction vector z. Second is surface. Okay, surface area. So for Cartesian, x, y, z. Okay, for cubic, we have surface 1, 2, and 3. Three surface. Surface at x axis, surface y axis, and surface z axis. For surface of x axis, we call dsx. Surface at axis is equal to, okay, this surface. Okay, how to find that surface? Okay, the changes of, okay, this part, this length, this width is equal to dy. Y axis. This one is y axis, and then up is z axis. Z axis, y axis. So to the right, so means that is y axis. That one is to the top, z axis. So surface area at vector x is equal to dy times dz. Okay, this one is at x axis. This size surface. Next is the surface x y axis, dsy. S for surface, y for axis, y axis. Okay, at this axis. At that axis. Okay. Surface at y-axis. Width time height. Height is z. The one is x. dx time dz. Y vector. Third one is surface. Surface at z-axis is equal to, okay, we have this time this area. This length time width. This length is equal to dx. This length is dy. So dx times dy. That is z vector. That is formula for differential surface of the Cartesian coordinate. Next is for cylindrical coordinate. This one is r, delta r. Okay, again, changes of r is delta dr. Changes of phi is r dv. This one is arc length. Changes of z is equal to dz. Sorry, dz. Surface for z is equal to r here, and also we have r, and also we have phi, r and phi. So for r is dr, phi is r dv. So means that the surface for z is equal to r times, dr is for r, dr for arc length is equal to r dv. So dr times r dv equal to, so this one is z as this, so z as this, r dr dv. That one is for circle part of the rectangle. Okay, next is we have a surface at phi. D as surface phi is equal to direction of phi r times z. Okay, r times z. R is dr times dz. That is direction of phi. This is okay. Okay, this one. Like this. This we call a direction of given surface, surface one. Direction of r. Direction of r means that this length is arc, this length arc times this one. This one is z. Z is this. So arc is equal to r d phi times dz. This line, this area. This area. So d surface r is equal to r vector r d phi times dz. Okay, this one is surface area for cylinder coordinate. Next is volume. Volume is very easy because for Cartesian we have x, y, and z. So dx dy and dz. So means that volume, differential volume is equal to dx times dy times dz. For cylindrical, we have dv is equal to r, phi, and z. R is dr, phi is equal to r dv, z equal to dz. So volume for cylinder will be equal to dr times r dv times dz. The third coordinate is spherical, like this, y, z, x, z. The coordinate for spherical, we have r, theta. This one is r sine theta. This one the phi. The coordinate will be equal to r, theta, and phi. That is coordinate for spherical. Spherical coordinate, we have r. So the changes of r we call, okay, this is r. Okay, changes of r is here. This is r. So changes of r will be here, dr. Changes of theta, z coordinate. This is r. This is theta. So let's say the changes of theta, here is d theta. This is r, arc length. This length. Okay, changes of theta cos this length is equal to r is r radius times time angle d theta. This one for okay r d theta. Changes of dr equal to dr, and then phi is phi. Okay, phi is between z x axis and r sine theta. This is phi. Okay, changes of phi is here. This one, d phi. So this arc will be equal to this length times d phi. R sine theta d phi. R sine theta d phi. This is length of arc due to changes of phi equal to r sine theta. Okay, r sine theta is this length times changes of phi. Changes of phi equal to r sine theta d phi. Differential length of spherical will be equal to dr plus r small r d theta plus r sine theta d. This one is direction of r, direction of theta, direction of phi. This is we call differential length. Next is differential surface, ds. Okay, so for r, this one, we take this one times this one. Okay, r d theta times r sine theta d phi. Let me check. Sorry. I have. Okay, sorry. This one is d phi. Okay. This one is R, capital R. Phi is here. Line is R d theta, okay? R d theta here. R d theta. I'm sorry, R d theta. R d theta. R d theta. So it will become direction of R square sine theta d theta d phi. Okay, now it's surface direction of theta. We have for theta, we just make theta become constant. And when theta become constant, take this one and this one. Theta constant, so dr times r sine theta d phi. Surface in theta direction. Then the surface in phi direction is will be equal to, direction is here, so we take this one times dr. R d theta times dr in phi direction. Differential surface area ds for spherical coordinate. Okay, last one is differential volume. We just take all differential. So dr times r d theta times r sine theta d phi. R and R we can combine, it will become R square equal to R square sine theta d theta dr and d phi. That one is differential length, differential length, differential surface area, and differential volume for Cartesian, for cylindrical, and for spherical. It's line integral. Okay, what is line integral? A line integral in calculus is a method of integrating a function along a curve. Okay, this is the vector field integral work calculates work done by a force along a path in electromagnetism. Let's say this path go here, so work done by a force along the path in electromagnetism. For example, river here, river, and water flow. This is current of the water, river. And then we want to swim across, swimming. And we swim across the river. When we swim it, the swimmer will burn off calories. So this calorie we call work that this swimmer need to cross the river due to this the flow of water, the direction of current flow. So this is what we call line integral. Line integral determine the total work that the pass from here. You want to go until here. So the total work that has been done by this point or this point. done by a force along a path in electromagnetism. Okay, this is electromagnetic. In my example, I show the river. So the force by water flow. In this case, the force by electromagnetic. And same goes to this example too. There are three types of integral. For example, we have a simple, this one is x, 1D for 1D, one dimension. Let's say this is fx. So this one is a surface of this 1D. So how to find surface? Surface will be equal to, let's say this A and B. So a surface equal to, we integrate from A to B. Okay, that's x, so dx. This one is dx. Fx. So fx times dx. This one for single integral. Let's say for 2D, we have x axis and y axis. This one is our f, x. Equation for y axis, like this, along y axis, and also along for axis is here. This is fx, this is fy. Okay, we can combine. This become PD. Okay, 2D for 2D. From this one to this one. Okay, this one. Let's say this is the area here. Okay, this one. Say this one is A, B, C, and D. So to find the volume under the surface, we can double integral. This one is single integral. So for double integral, we can integral x-axis and then y-axis. Yes. So for x-axis, x is A and B. So we can combine fx and fy to be fxy for AB dx due to changes in x-axis, and then dy. dy is C and D. So C and D, C, D, dy. This one we call double integral. The next one is triple integral. 3D, we have Z, X, and Y. Just a simple Cartesian. We have Fz, Fy, Fx. Fy along y-axis, Fz, z-axis, Fx, x-axis. A, B, C, D, E, F. Okay, A, B, F, X, Y, and Z. AB is at x-axis, so dx, CD, dy, EF, dz. This one we call triple integral. Example 4.1, we have this surface. This one is arc. First, we know that this one is cylindrical. Cylindrical coordinate. For coordinate, we have R, P, and also Z. Okay. R is dr, P is r dv, z is dz. So means that for this one is r dv. This one is z, z axis. Vertical one is z axis. So this one dz. So our integral will become, we have to do double integral. We have dz and also dv. So the surface ds will be equal to, okay, r dv dz. Okay, we can put either one. Oh, if you want to take, okay, that's double integral. So for r is equal to 5 to radian, 60 degree and 30 degree to radian. So how to find for radian? So 60 equal to pi over 3, 30 is pi over 6. Okay, the solution is here. Just follow the solution, take out r, and then we d5 we integral d5, we got 5. ds equal to 0, 3 pi over 3 pi over 6 r dv dz. So it's equal to, we can take out r, 0, 3, so pi over 6 pi over 3 dv and dz. So this will become r 0, 3 v pi over 3 pi over 6 dz equal to r, sorry, r is 5. Just replace 5 here. 0, 3 pi over 3 minus pi over 6 dz. So it will become 5, 0, 3 pi over 6 dz. So finally you get 5 pi over 2. And next is calculate rho ds over given surface. This is a cylindrical changes of, okay, changes of phi. This one is changes of z, dz. So r, phi, and z are dv, dz. So our equation will become, there's a few example. I think you can go through this example one by one. This one is for Cartesian, x, z, sorry, y and z, y and x means that z is constant. So we have dy and dx. So surface is equal to dy 2, 4, dx 1, 2. 1, 2 dx 2, 4 dy equal to 2, 4 or dx x 2, 1. Sorry, 3, yeah? This is 3, sorry, 3. 3, 1. This is dy. So 3 minus 1 equal to 2. Equal to 4, 2, 2 dy. 2, 4 dy equal to y 4, 2. 4 minus 2 equal to 2. 2 times 2 equal to 4. Okay. The area for this equal to 4. Okay. Actually, this one is 4 minus 2 equal to 2. 3 minus 1 equal to 2. So 2 times 2 equal to 4. Okay, next one is cylinder. Cylinder, however, this one is, this surface is Z is a constant. So we only have arc here. Arc times, where is this? Where is this? Not Y, R. This is R. Radius. Okay, arc length is equal to R, P, and Z, coordinate for cylinder. R is dr, R dv, Z is dz. So dr times R dv. R dv times dr. In this case, it's E. The given is E equal to ZR. We just put R times R, one more R. Is R. So we get R squared dv and dr. Then do integration. I believe you already learned in your mathematics. Just this one is just simple integration. Integration one by one. R with dr, and then this dv. Spherical, we have R, theta, and phi. This one is R d theta. Phi equal to R sine theta d phi. This one is equal to dr. R exists, so R is constant. So the variable will be theta and phi. It's the variable. R d theta times R sine theta d phi. R square sine theta d theta d phi. So do double integration. Okay, the angle is between 30 and 60. 30 is equal to pi over 6. 60 equal to pi over 3. So just replace pi over 6 and pi over 3. The one is theta. For phi, okay, we know that this is complete circle. So for phi is equal to from 0 to pi. 360 degree, eh? From 0 to 360 degree, for so 0 to pi. So the range is between this one and this one. Pi over 3, pi over 6, 0 to pi. Then you can continue like this. Okay, I think that's all for today's lecture. Any question?